Okay, in this video, we're going to be continuing our conversation about mole conversions and the mole heart, but we're going to focus primarily on conversions using our molar mass and then doing multiple step conversions. So conversions in which we have more than one conversion factor. So first of all, let's look at our molar mass conversions and what molar mass is. Remember, 1 mole is equal to 6.02 times 10 to the 23rd, but 1 mole of any substance is equal to its molar mass, or its atomic mass in grams. So for example, example number 4 asks to find the molar mass of the following: sodium, oxygen gas, and glucose, C6H12O6. So let's look at sodium. It wants us to find the mass of 1 mole of sodium. Essentially, that's what it's asking when it asks us to find the molar mass. The molar mass is the mass of 1 mole of each of these substances. So the mass of 1 mole of sodium is equal to its atomic mass in grams. So we can actually round up. So the mass of 1 mole of sodium is 23 grams, because its atomic mass is 23 or 22.99 atomic mass units. So if I have a mole of sodium, that 1 mole of sodium, which is going to be 6.02 times 10 to the 23rd atoms of sodium, is going to actually weigh 23 grams. Or, and to write this properly, the molar mass is 23 grams per mole. So to find my molar mass of oxygen, in that case, I have O2. So I actually have 2 atoms of oxygen bonded together to form a molecule of oxygen gas. And if I look at my periodic table, the atomic mass of oxygen is about 16 AMU, or 16 atomic mass units, which means that the molar mass of 1 atom of oxygen is 16 grams per mole, but I have 2 atoms of oxygen in my molecule. So 16 grams plus 16 grams. So 1 mole of oxygen gas, 1 mole of O2 molecules is actually going to weigh 32 grams. So my molar mass of oxygen gas is 32 grams per mole. And finally, if I look at my glucose, I have a lot more than just 1 element. I actually have 3 different elements: carbon, hydrogen, and oxygen. So I'm going to have to do the same thing that I did with my oxygen gas. And to find the molar mass of my glucose, I have to add up the molar masses of each of my individual components. So first I have to look up my molar mass of carbon, which has an atomic mass of 12 AMU. So my molar mass of carbon is 12 grams per mole. But I have 6 of those, so I have to multiply it by 6 since I have 6 carbons. My atomic mass of hydrogen is 1 AMU, so my molar mass of hydrogen is 1 gram per mole, but I have 12 hydrogens, so I have to multiply that by 12. And then finally, my oxygen again, I know that my atomic mass of oxygen is 16 AMU, so my molar mass of oxygen is 16 grams per mole, but I have 6 oxygen. So I have to take my 12 times my 6 for my carbon, plus my 1 times my 12 for my hydrogen, plus my 16 times my 6 for my oxygen, because I have to take the molar masses of each of the components, multiply it for each of the elements, multiply it by the number of atoms of each of those elements that I have, and add them up to get my molar mass for my entire molecule. So when I put this into my calculator, I get 100 grams per mole. So 1 mole of C6H12O6, 1 mole of glucose is going to weigh 180 grams. So to review, the molar mass is the mass of 1 mole of a substance, and we're usually going to measure that in grams. The molar mass of an atom is its atomic mass in grams per mole. So for example, our atomic mass of carbon is 12 AMU, so its molar mass is 12 grams per mole. And the molar mass of a molecule is the sum of the molar masses of its elements. So for example, the molar mass of water, H2O, is going to be the sum of the molar masses of the 2 hydrogens and the 1 oxygen. So we have 2 hydrogens, each with a molar mass of 1 gram per mole. So 1 times 2, since I have 2 hydrogens, plus my 1 oxygen, which has a molar mass of 16. So my molar mass of water is going to be 18 grams per mole. And this is an essential step to know how to do in order to do the rest of our conversions for moles. So now let's practice and take a look at how we use the molar mass when doing our conversions. So example number 5 asks us to find the mass of 4.5 moles of N2. So we always start with what we're given, which is 4.5 moles of N2, and I'm going to write N2 in here so that I remember that I'm working with a diatomic, because then I know, looking at my map, I'm starting at moles of N2, so I'm right here in the middle of my mole heart, and I need to go to mass. So I need to go right here, and I need to use my molar mass, which I'm going to need to calculate. So in order to keep track of what I have to calculate, I'm going to write N2, and what I have needs to go on the bottom because it's what I need to get rid of. So moles of N2 goes on the bottom, and looking at my mole heart, I know it's going to be a 1 conversion problem, so I can go right from moles to grams of N2. And whenever I'm doing moles conversions, it's going to be in terms of 1 mole, and my molar mass of N2, I have 2 nitrogens, and the atomic mass of nitrogen is 14, so my molar mass of nitrogen is 14 grams per mole, but I have 2 of them. I have N2, so my molar mass of N2 is going to be 28 grams per mole. So when I put this into my calculator, 4.5 times 28, I get 126 grams of N2, because my moles cancel and I'm left with grams. So 4.5 moles of nitrogen gas is going to weigh 126 grams. Now example number 6 is a little trickier, but I wanted to show you something like this so you could see how to calculate something with a little bit more complicated of a formula. So example number 6 asks how many moles are in 567 grams of AlNO3 So I look at my map and I'm starting at grams, so I'm starting at mass, and I need to go to moles. So it's going to be a 1-step conversion. So start with what I'm given, which is 567 grams of aluminum nitrate, AlNO3, and I'm going to multiply by my conversion factor, which is going to be grams of aluminum nitrate on the bottom and moles on the top, because what I have is what I need to get rid of, and what I need to get to needs to go on the top, and I know it's a 1-step conversion from my mole heart. So 1 mole equals some amount of grams of AlNO3. So in order to figure out how many grams, I have to calculate its molar mass. So my molar mass of my aluminum is 27 grams plus, and this is where it gets a little tricky, I have to calculate the molar mass of my nitrate. And even though this is a polyatomic, we're going to calculate the molar mass the same way we would any other molecule, just by using our periodic table. So our molar mass of nitrogen is 14, I'm going to put this in parentheses, plus my molar mass of oxygen, which is 16, so this is for my nitrogen, and then my molar mass of oxygen is 16, but I actually have 3 of them, so I have to multiply that by 3. And then I have 3 of these nitrates in order to balance the charge with my aluminum. So I have to multiply this whole thing by 3. So put double parentheses there. And I suppose this should be triple parentheses. So I'm going to have 14 plus 16 times 3. And I'm going to get 62. Oops. Let's do 27 for my aluminum plus 62. So that's the molar mass of my nitrate, but I have 3 of those. So 62 times 3, which is 186. So I have 27 plus 186. And I get 213 grams per mole is my molar mass of aluminum nitrate. So this is 213 grams. So now I take my 567 divided by 213, and my grams are going to cancel, and I'm going to be left with 2.66 moles of aluminum nitrate. 3. Okay, so the same procedure applies. It's just a little more complicated when you have a polyatomic and have multiples. But that's how you go from grams. So in 567 grams, I have 2.66 moles of aluminum nitrate. The last thing I want to look at in this video is how to do multiple step conversions. So example number 6 asks how many molecules are in 7.56 grams of NCl3, nitrogen chloride. So if I look at my map, I'm starting in grams, so I'm starting up here at my mass, and I need to go to particles, which includes my molecules. But I can't go directly from mass to particles. There's no conversion factor that connects those two. So this is actually going to be a 2-step conversion. I'm going to go from mass to moles, and then moles to particles, or molecules in this case. So using my mole heart, I know this is going to be a 2-step conversion. But the process is going to be very similar to what we've been doing. So start with what you're given, because we're still using factor label method. So 7.56 grams of NCl3. And our first conversion, I know I'm going to be going from grams to moles. So I have to convert to moles first. So my grams are going to go on the bottom and my moles on the top. And 1 mole of NCl3, I need to find my molar mass. So I find my molar mass of nitrogen, and it is 14. So 14 plus my molar mass of chlorine, which is 35.5, but 35.5 times 3 is 106.5, so I have to add my 14 to 106.5, and I get 120.5, and so now my grams cancel, and I'm at my moles section. But I can just keep going because they didn't ask for moles, they asked for molecules, so I have to keep going. So now I have my moles on my top, and that's what I want to get rid of, so I need moles on the bottom. And they asked me to get to molecules. So my molecules needs to go on the top. And if I have 1 mole, so now that I am here, I need to go to my particles or my molecules. And I know that in every 1 mole, there is 6.02 times 10 to the 23rd molecules. And my moles cancel out, and I'm left with molecules. So I'm going to take my 7.56 divided by my 120.5 times 6.02 times 10 to the 23rd. And I put that in my calculator and I get 3.78 times 10 to the 22nd molecules of nitrogen chloride. So there's 3.78 times 10 to the 22nd molecules of NCl3 in 7.56 grams of NCl3. And let's do one final example for today. So example 7 asks how many liters would 50 grams of CO2 occupy at STP. So I'm starting at grams, so I'm starting back at my mass, and they want to know how many liters. I'm going down here to my volume. So I'm going from mass to volume, but again, there's not a single step that can take me right from mass to volume, so I have to convert from mass to moles and then from moles to volume. So this is going to be a two-step conversion process. So always start with what you're given, which is 50 grams of CO2, and times your first conversion factor, so grams on the bottom, and I know I'm going from grams to moles, so I need moles on the top, because that's what I'm converting to, and 1 mole of CO2 is my molar mass of carbon is 12, and my molar mass of oxygen is 16, but I have 2 of them, so 16 times 2. So 12 plus 32, and I get 44. So my molar mass of CO2 is 44 grams per mole. And now my grams have canceled. So now I'm left with moles, but I need to get rid of my moles because I need to be in liters. So my moles go on the bottom, and on my mole heart, I'm right here in the middle. And I need to get to my volume, so I need to use my molar volume. So my moles on the bottom, my liters on the top, and my molar volume states that 1 mole of gas has a volume of 22.4 liters, always, as long as it's a gas. And so now I can put this into my calculator, and my moles have canceled, and I'm left with liters, which is what I was after. So 50 divided by 44 times 22.4. And I get 25.45 liters of CO2 gas. And so from this video, you should have learned how to find the molar mass of both atoms and molecules, and how to do multiple step conversions using the factor label method and your mole heart to go from one part of the mole heart to any other part, even if you have to do multiple steps and use multiple conversion factors. Please write down any questions you have, bring them to class, and we will go over them.